Alright, let's continue our discussion of writing reactions, and what we're going to do in this podcast is take a look at double replacement reactions. And we're going to do the same thing that we did with single replacement reactions. In other words, we're going to write the reaction, in other words, predict the products of the reaction, and then determine if the reaction happens. So for example, let's say we had sodium chloride and it reacts with lithium fluoride. We could write the reaction, sodium fluoride and lithium chloride, as the products, but that doesn't mean that that reaction would actually take place in real life. Okay, so let's write the reaction, and again, you want to be comfortable writing formulas from names. So, silver nitrate. And silver is one of those compounds that you should just know the formula, or the charge I mean, is 1 plus. So we have silver nitrate, and that's reacting with sodium chloride. So as we talked about in the types of reactions vodcasts, we're going to take the two cations and we're going to switch them. In other words, silver is going to form a compound with the chloride. The sodium is going to form a compound with the nitrate. So we have silver chloride plus sodium nitrate. Alright, with double replacement reactions, now we have to include those subscripts. In other words, we have to indicate, are these solids, liquids, gases, or aqueous solutions. Typically in a double replacement reaction, the first, or I should say the two reactants, are aqueous compounds. In other words, when you put those in solution, they should dissolve. The way you determine the subscripts for these compounds is something that we call the solubility rules. As with the activity series for single replacement reactions, you should have the solubility rules handy while you are writing these reactions. Or you could memorize the rules, but it's a little easier to have them handy. Okay, so these are the basic rules, and you're going to see them written in this form, and you'll also see them written in chart form. Personally, I think using them in chart form is easier. Let's go through what this means. Let's say you have an ion that contains nitrate. In other words, let's say it's silver nitrate. Nitrates are all soluble without any exception. So any compound that you see that contains nitrate, we're going to consider soluble. Now, in real life, there's exceptions to a lot of these rules. However, these are the rules that we're going to use. So let's say, for example, it were chloride. And let's use two scenarios. Silver chloride and sodium chloride. Chlorides are all soluble except silver chloride, mercury chloride, and lead chloride. So this one would be insoluble, this one would be soluble. Now, soluble means that it dissolves in water and forms ions. This is going to be important for when we write double replacement reactions. If something is soluble, it's going to get the aqueous subscript. In other words, if it's soluble, it dissolves in water, forms an ion, so we're going to say it's aqueous, dissolved in water. If something is insoluble, in other words, it won't break apart, so it's going to remain as a solid. So we're going to give that the solid designation. So when we use the solubility rules for compounds, what we're trying to do is determine if they're soluble to give them an AQ subscript, or if they're insoluble to give them a solid subscript. So when we look back at our chart, or I'm sorry, when we look back at the descriptions say the same thing. In other words, most nitrate salts are soluble. I want to point out a few things here. A salt, I think we've mentioned this before, is simply another name for an ionic compound. So when we talk about these ionic compounds, another word for those are salts. So okay, let's do some of the examples. We've got double replacement reactions, and again, the first thing we want to do is determine the subscripts. So we've got sodium sulfate. And if you look on your solubility rules, what you'll find is that group 1 metals are all soluble. So sodium sulfate is going to be soluble. On the other hand, you could look at the sulfate in the compound, and what you can determine is that sulfates are soluble with a few exceptions. Sodium sulfate is not one of the exceptions. You'll see, all right, so if that's soluble, that's going to get the AQ designation. Barium nitrate is also soluble, so it's going to get the aqueous designation. Let's switch the cations, so we're going to form sodium nitrate and barium sulfate. That's a 4. Nitrates are soluble, so that's going to get the AQ designation. Sulfates, again, are soluble, except barium sulfate is one of the exceptions. So, if it's insoluble, it gets the solid designation. The way you determine if a double replacement reaction happens is if one of the products is something other than aqueous. In other words, something has to change in the reaction. We have 2 aqueous compounds forming an aqueous and a solid. So something changes, so that reaction happens. If everything was all aqueous, then the reaction wouldn't happen. So for example, sodium nitrate, nitrates are all soluble, so that gets the AQ. Ammonium compounds are all soluble, so that gets the AQ. Cations switch, so sodium chloride plus ammonium nitrate, sorry, my 4s keep looking like 9s. That's soluble, so AQ. This is soluble, so AQ. So everything is aqueous, so that reaction does not happen. Let's take a look at the next one. We've got zinc chloride. If you look at your solubility rules, you'll see that chlorides are soluble. There's a few exceptions, but zinc is not one of them. So aqueous. Carbonates are generally insoluble, but it's with a group 1 metal, so it's soluble, so AQ. Write the formulas. Zinc is another one of those that you should just know the charge. Zinc is 2+, so it would be zinc carbonate and potassium chloride. Zinc carbonate is insoluble, so it's going to get the solid. Calcium. Potassium chloride is soluble, so it gets AQ. So one of them changes, so that reaction does happen. Let's take a look at the last one. We've got ammonium chloride plus silver nitrate. Soluble, so AQ. Soluble, AQ. Let's write the products. Silver chloride plus ammonium nitrate. Now ammonium nitrate is aqueous, or I should say it's soluble, so it gets the aqueous designation. Silver chloride, again, most chlorides are soluble, except silver is an exception. So that's insoluble, so it gets the solid subscript. So one of them changes, so that reaction does happen. Okay, let's take a look at a couple more examples. Again, sodium sulfate, if you use your solubility rules, the sulfates are generally soluble, with a few exceptions, sodium not being one of them. So it's soluble, so that's aqueous. Nitrates are soluble, so that's aqueous. The products would be sodium nitrate, which is soluble, plus barium sulfate, which is insoluble, so it gets the solid. Now what we want to do with this after we have this written is write what we refer to as a net ionic equation. what you want to do first of all is balance the equation. So we're going to put a 2 here, and I think that's balanced. It is. The next step you want to do is write everything in its ionic form, which means everything that's aqueous we're going to break up into its ions with the proper number of ions. So for example, here there's 2 sodiums. So we're going to say 2 sodium ions and 1 sulfate polyatomic. So we've taken this compound and we've broken it up into the cation and the anion part. Same thing with the barium nitrate. We've got 1 barium ion and 2 nitrate polyatomics. Draw your arrow. Sodium nitrate is aqueous, so we have 2 sodium ions and 2 nitrate polyatomics. Don't forget your charges. Now barium sulfate is solid, so we are going to write that as barium sulfate. Alright, the next step in this process is everything that is the same on the reactant side and the product side we cross out. The reason is if it doesn't change, we're not interested in it. So we have the sodium ion as a reactant, it's still an ion as a product, so we're going to cross that out. The sulfate, on the other hand, here it's an ion, but here it's part of a compound, so we're going to keep that. So we're going to write that here. The barium, the same thing. Here it's an ion, but here it's part of a compound, so we're going to keep that. The nitrates, again, the 2 nitrates are ions as reactants, ions as products, so they don't change, so we're going to cross those out, and we're going to write our product here. So our net ionic equation is the end result of crossing out everything that doesn't change. In other words, it tells you the important part of this reaction. If you take 1 sulfate polyatomic and 1 barium ion, they come together to form this solid. These other things just stay as ions in solution. That is what we refer to as the net ionic equation. The things that we cross out we refer to as spectator ions. Alright, let's take a look at the next one. Sodium nitrate, aqueous because it's soluble. Ammonium chloride, aqueous because it's soluble. The 2 products would be sodium chloride and ammonium nitrate. That is aqueous. That is aqueous. So everything is aqueous. So if we were going to write this in ionic form, everything would be an ion on the reactant side and the product side. So everything is going to cross out here, and as we said before, that reaction would not happen. Alright, let's take a look at 2 more examples. Zinc chloride, again, if we check our rules, our chlorides are soluble, with a few exceptions, zinc not being one of them, so we're going to write that as aqueous. Potassium carbonate, also soluble, so it's aqueous. Write our products, zinc carbonate and potassium chloride. Now the carbonates, again, we said those are insoluble, so that's going to be a solid. Potassium chloride, soluble, so it's aqueous. Let's make sure it's balanced. We're going to need a 2 there, and I believe that's balanced. Alright, let's write everything in the ionic form. So we have zinc, 2 plus 2 chloride ions, plus 2 potassium ions, plus the carbonate polyatomic. Now zinc carbonate's a solid, so we'll write that as a solid, zinc carbonate. In other words, it doesn't break up into its ions, so we're going to leave it like that. Plus 2 potassiums, plus 2 chlorides. The zinc ion is an ion as a reactant. It's part of a compound as a product, so that changes, so we're going to include that. 2 chloride ions as reactants, 2 chloride ions as products. They don't change, so we'll cross them out. 2 potassiums, 2 potassiums. The carbonate we're going to write because it's an ion as a reactant. It's part of a compound as a product. So our net ionic equation is the zinc ion reacts with carbonate to form zinc carbonate. Our spectator ions are the chloride, potassium, chloride, potassium. All right, let's do one more. Ammonium chloride, aqueous, plus silver nitrate, aqueous, forming ammonium, nitrate, aqueous, and silver chloride solid. Let's write everything in ionic form. We've got the ammonium ion, or polyatomic, plus chloride, plus silver, plus nitrate, yields ammonium plus nitrate. Silver chloride's a solid, so we leave it as a solid. Cross out the spectators. So we have the chloride ion reacts with silver to form silver chloride. Now these are going to take some practice. So as we work through this unit, make sure you're practicing writing these reactions as much as you can.